So this video is going to cover method of sections. So method of sections is really great when you don't want to find the force in every single member. So for this example, we actually only want to find the forces in LK, EP, and EF. To start with, let's go find out where in our truss those are located. So LK, EP, and EF. Those are the only ones that we care about. So when we're doing method of sections, we want to make a cut that's going to go through, ideally, those particular members. So I'm going to make a cut right here. Now the question is, do you take the right side or the left side of the cut to be your free body diagram? And that really depends. In this example, you could do either one. It doesn't really matter. I'm going to specifically choose the left side. So if I want to do the left side, I need to find the reaction forces on the left side. So my reaction forces are going to be AX and AY. So to start with, the first thing that we're going to do is we can sum the forces in the X direction and set it equal to 0. And we notice that there is only AX in the X direction. So AX is 0. Easy enough. Next, we need to sum the moments. And the point that we're going to take the moment about is going to be joint I. That's going to give us AY. So we're going to sum the moments about I and set it equal to 0. And we're going to choose counterclockwise to be positive because that's just what I like. So to start with, we're going to start on the left side and work our way to the right. So we have AY, and AY is going to be going the wrong direction. So negative AY, and he is times 2, 4, 6, 8, 10, 12, 14, 16 meters. Oh boy. Then we have a positive 2 kilonewtons, and his distance is going to be 2, 4, 6, 8, 10, 12 meters. Then we have plus 4.5 kilonewtons times 2, 4, 6, 8 meters. Then we've got positive 4 kilonewtons times 2, 4, 6 meters. And then lastly, a positive 2 kilonewtons times 2, 4 meters. Okay, a lot of meters there, a lot of forces. So we're going to find that AY is equal to 5.75 kilonewtons in the positive direction. Cool. So next thing that we're going to do is we're actually going to make this cut and we're going to redraw our free body diagram. So here is the cut that we've created with our little free body diagram. Our free body diagram on the left side specifically. And we just found that AY was 5.75, so we'll go ahead and write that in, 5.75 kilonewtons, and we said he was going up. So now we have the cut. Our cut went through our member forces LK, EP, and EF, so we're showing those ones. Now method of sections doesn't just have to do some of the moments, but some of the moments is ideal when you want to isolate one force. So if I want to, say, find the force LK, I want to try and find a point to take a moment that's going to get rid of the forces EP and EF. And the thing that they both have in common, I can either follow the direction that they're going forward or backward. So I'm going to follow them both backward, and I'm going to notice that they both have joint E in common. So I'm going to start by summing the moments at E. And if I do that, the only thing that I have as an unknown is force LK. So we can do that. So we're going to sum the moments about E, take counterclockwise to be positive, set it equal to 0. So we have our 5.75 kilonewtons, and he's going to be going in the wrong direction. So negative 5.75 kilonewtons, times the distance he is to E is 8 meters. Then we have our 2 kilonewtons. We're starting from the left side, working our way over to the right. So we have our 2 kilonewtons at C. It's going to create a positive moment. So plus 2 times his distance is 4 meters there. The 4.5 right here does not create a moment about E. He's acting at point E. He's in line with point E, so he does not create a moment. So he's not included. However, we do have force LK, and LK is going to be going in the wrong direction, so we have minus force LK times his distance. Vertically, there is 4 meters. So we're going to get that force LK is equal to negative 9.50 kilonewtons. And that is in, well, technically that is 9.5 kilonewtons, 50 kilonewtons of compression. Now, you can go through and instantly start by redrawing all of your arrows. I don't recommend doing that, but you could. But technically our final answer is in compression. So if we leave our free body diagram the way that it is, with the direction of our arrows that we've already drawn, then we just need to make sure that we're including the positive or negative sign. So compression is a negative, so if we are going to include LK in anything else, we're going to include it as a negative 9.5 if we're assuming the current direction's drawn. Now, technically, you don't just have to do everything as some of the moments. You can do some of the forces in the X direction and some of the forces in the Y direction as well. So there is that. But if you really wanted to be cool and take moments, technically, another one that we could find is force EF. If I want to find force EF, I want to find the point that force EP and LK have in common. So let's go back up here and look. So EP and LK both have in common point K. Even though he's not on my free body diagram, I could sum the moments about point K. Now that would have to include all of the rest of the things here. So that's not very fun, to be honest, but you could do it. If you're a big fan of summing moments, you can totally still do that. So let us actually just do things a little bit simpler. Okay, I notice that I have force LK. That's great. I notice that I have forces horizontally and vertically. That would be nice. But if I do forces horizontally, I have EP technically has a vertical and horizontal component, and EF also is horizontal. So the best thing to do in this case is to sum the forces in the vertical direction first. And to do that, we're going to kind of need to figure out some information about force EP. So just a little note about EP here. If we're looking at it, we've got 2 meters vertically, and we've got from EF 2 meters horizontally. So we can actually find the length of EP, right? So we have 2 meters vertically and 2 horizontally, and we know that a triangle in this situation, a 2 would be a 2 square root of 2 for the length. So EP's vertical component is going to be 2 over the square root of 2. So we can sum the forces in the Y direction and set it equal to 0. We have AY going up, which was 5.75 kilonewtons. We have at joint C, we have minus 2 kilonewtons. And then we have at joint E, technically he's on our diagram, minus 4.5 kilonewtons. He wasn't included before because he doesn't create a moment, but he is in our diagram. He is going in the vertical direction, so we are going to include him. Then we have a positive force EP. Again, we need the vertical component. The vertical component is 2 over 2 square roots of 2. Cool, so we set that equal to 0 and we can solve for force EP. Force EP is going to be 1.06 kilonewtons in tension. So there's force EP. And now that we have force EP, we can go ahead and we can actually solve for our forces in the x direction. So sum of the forces in the x direction, set it equal to 0. AX was there, but AX was 0, so he really doesn't matter. So all we have is force LK. He's positive in the way that we drew it, so we're going to leave him as a positive value. When we plug him in, we're going to plug in the -9. And then we also have force EF. And then we also have all of these in the same direction. Right, we have force EP, but we need the horizontal component, and the horizontal component is also going to be 2 over 2 square roots of 2. So again, remember that when you plug in for force LK here, we're plugging in a -9.5. And when you plug in for EP, this is 1.06. So we're going to get that force EF is equal to 8.75 kilonewtons in tension. Cool, so we found our 3 forces, LK, EP, and EF. And the other part of the problem was asking us to list the zero force members. So what we want to do now is figure out which one of these wonderful members is a zero force member. So let's see if we can figure out any zero force members from this diagram. What we want to do is isolate some joints. So let's isolate, say, joint L. What's going on at joint L? If we just break joint L into its own free body diagram, if you are to sum the forces in the y direction, you only have one member. So that one member must be equal to 0. So this member is a zero force member. Let's do the same logic over here at joint B. At joint B, if we draw a free body diagram, it's an inverted T. So if you sum the forces in the y direction, you're going to get that your y1 here is 0. Again, you can do the same thing at joint D, right? So at joint D, this is also 0. And at F, you might be thinking, oh, we can do the same thing, but actually at F, we have a downward force. So in this instance, no, that one is a little bit different from the rest of them. But if you go look at joint H, he is the exact same as everybody else. He's a zero force member. So far we've identified 4 of them. Now, once we've identified those, and we're going to write these down really quick, we've got BN, we've got DO, we've got LE or EL, and we've also got HJ. It's really nice if you can go through and actually erase the member. I know, way easier said than done, but if you erase those members, now this is your updated truss, because remember, it's a zero force member. So if it's a zero force member, it technically doesn't exist. So now let's see if there's anything else that may look very similar. Like for instance, joint N. Joint N looks like this. Now you might be thinking, well, if you sum the forces in the x direction or sum the forces in the y direction, we've got 3 different forces. But since these are collinear, these two at the angle there going from A to M, since those are collinear, if you were to rotate this and have a new, call that maybe the x prime and this the y prime direction, if you were to rotate that, well, now if you sum the forces in the y direction, the y prime direction, now you don't have anything other than that one member. So he is going to be a 0 force as well. So anytime that you're seeing those two collinear forces and you have a third one coming off, and it really doesn't matter if it's perpendicular or not, but anytime that you see that, it's going to be a 0 force member. So same thing with joint O over here. We have a diagonal and one coming off. So again, you can rename the directions x prime and y prime, and you're going to find that this is a 0 force member. Moving on over, we've also got joint J. Joint J is doing the same thing, and literally we didn't even erase the picture. It's the same diagram. So again, this is a 0 force member. So we'll update our list really quick. And we've got CN, CO, and GJ. So that's a total of 7 0 force members. If we want, we can go ahead and erase them. And we can look, do you see any more of this situation? Now again, C does not count because he still has his force down here. So if you sum the forces in the y direction, he still has a force. Same with F, he still has a force. So that joint O is effectively gone at that point. And so is N, and so is J. So that's all of our 0 force members. And again, we use the method of sections to find the forces in those 3 members that we were asked to find. So method of sections is supposed to be a quick way to figure out just a few important pieces of information and not necessarily the whole truss.